So our vision has been, how do you collect water from air anywhere in the world, not just even the red regions, but also the blue regions at any time of the year. So all year round. So I want to show you our results in that direction. But first, I want to show you why it is difficult to trap water from air and collect it. Okay, so here's a psychrometric chart. I'm plotting here on the y-axis the water vapor in air grams per cubic meter versus temperature. And I have colored two regions here. The green region is where, let's say, you have high humidity, and this yellow region or pink region is where you have low humidity. You see here, this is the line for relative humidity, 10%, 20%, 30%, 40%, and so on, up to 100%. As you reach this line, you get liquid water. Okay, so I want to show you what happens if I'm in a city, let's say here in a city at 20% relative humidity and 30 degrees Celsius. Let's say I want to cool that air to get the water out. To get to the water, to liquid water, to condense the water, I have to cool down that air from 30 degrees Celsius to 4 degrees Celsius. Okay, that's not very economical. That does not work, and it is not a viable way of generating water from air. However, let's imagine that I have the MOF that I just showed you, and I have the ability to trap the water in the pore and fill it up with water. What happens is that I'm creating humidity. Okay, so the MOF is taking up the water at 20% relative humidity, concentrating it into the pore, and now I have, let's say I have the MOF in a container, I have a humidity that could be up to 90%. Okay, so increase the humidity by virtue of having the MOF trap that water. Now, in order to get liquid water, I only need to cool down by few degrees, 4 degrees, from 30 degrees C to 26 degrees C. So if I can create a MOF that takes up water from low humidity, then I've solved the water problem in the arid regions of the world. And so this is the results that I want to show you. But first, as I said before, there's been many attempts to do this before. There are many materials that are now being examined, such as zeolites, polymers, hydrogels, even molecular crystals, simple salts. And none of them has emerged as a viable solution, because in order to have a good water harvesting material, you need to meet three very important characteristics. One is that the material has to have high capacity. If you're not storing a lot of water, then you have to do many cycles, and that requires energy. You need to have fast kinetics. Water has to be able to get in very fast and come out very fast. Otherwise, you have to wait a long time to get water. And definitely, your material should work at low humidity. This is the challenge facing in the world in terms of water stress. So these materials meet one or so, but they really fail a lot in the other categories. So we were investigating the carbon capture of MOFs. And when you capture carbon dioxide from the atmosphere, you have to separate it from water in the atmosphere. And so you need to understand what is the interaction of water with the MOF, just as much as you have to understand how carbon dioxide is processed in the MOF. So we were studying both molecules and trying to understand how the MOFs behave. And we made a discovery. The discovery was that this MOF is able to take up water. Let's focus on the red line here. Take up water at relative humidities around 20%. Okay, that's low humidity, and that's typical humidity in the desert. So that's one very important discovery. It means that the moth that we were using is able to pluck out water from low humidity. The second important thing is that the way the moth behaves when it's taking up water is in a cooperative fashion. So you have this very sharp step, and then as the pore gets saturated with water, of course, you get a flat uptake. Okay, so this step is very important because it maximizes the amount of water, my working capacity, the amount of water that I can not just put in, but take out. Now, the third very important observation that we made is that the water that goes into the pore can come out. This is now the green line. When I heat the material to 45 degrees Celsius, it comes out in the same way it went in. Okay, so when I looked at this, I immediately realized that this could be a material that can be deployed in the desert, where at night, when it's cool, it can trap the water, and during the day when it's hot, you can release the water. So unlike other materials like zeolites and other materials that take up water, they are extremely hydrophilic. Zeolites can take up water from low humidity, but you need to heat a zeolite up to 300 degrees Celsius to remove the water. Again, that makes it not a viable solution for harvesting water from air. But for a moth, you have the inorganic part, let's call it the hydrophilic part, and the hydrophobic part is the organic part. And this modulates how tightly water can bind to the interior of the moth. And therefore, we can modulate this strength very nicely, and which allows us to then have the water come out at lower temperatures. So we cycled water in and out of the pore, as you see here, over 80 cycles, leaving no imprint on the moth. Now, some of you may notice that after the first cycle, you see a slight drop in the uptake of water before it is stable in terms of uptake and release. This slight drop, when we look deeply into why is there a slight drop, initial slight drop, it gave us the secret for making moths for water harvesting. Let me elaborate on that. You can use X-ray, single crystal X-ray diffraction technique and neutron diffraction techniques to look deeply in the pores of the moth and locate where those very first water molecules reside in the structure. And then we look at their interactions with the structure. So you see here for this moth, we found the water molecules shown here in red bound to the metal oxide unit or to the inorganic unit. And then as more water comes in, they make up aggregates such as these cubic aggregates. And these, we find that these are the seeds onto which other water molecules come in and bind. So in fact, the water structure, these red spots you see here, are built up in the pore almost like ice, I would say ice chunks that fill the pores. And the key here is that the very first water molecules bind strongly to the metal oxide unit, and they act as a magnet to the water molecules that are in the air, bring them in and bind them and build the structure up of the water in the pore. So this was the key, the seeding effect, which we attribute to the excellent properties of the moth taking up water from low humidity air. Okay, so from the laboratory, we wanted to take this outside and show that in fact this works in the desert. So here's a device. This is a very small device that only has 2 grams of moth. Okay, it's a handheld device. And the way it works is that the moth is put in the container, and during the night, the moth is exposed to the air. Water from the air goes into the moth, and during the day, you close the container. And when the container is closed, you can expose it to the sunlight. And as the interior heats up, this is the interior of this box, shown here, 50 degrees Celsius, and increases 60 degrees Celsius, and so on. And you see small droplets of water that are beginning to grow. Okay, so this is basically a proof of concept that the moth works outside the laboratory at a humidity. In this case, the humidity was between 20 to 30% relative humidity. And so this was very, very exciting, because for the first time, it's very clear that one can trap water from air and take it out at very mild conditions with absolutely no energy input aside from sunlight. So we wanted to scale this up. So we scaled it up to a kilogram quantity of moth, and we changed the design of the device so that the moth, it's basically a box within a box design. The interior box has the moth, and that put inside a larger box. The larger box is open during the night to allow desert air to come in, and the moth trap the water from desert air. And during the day, you close the outside box, expose that to sunlight. As the interior heats up, water comes out of the moth and condenses on the walls of the box. That's roughly the principle of how this works. This is what this water harvester looks like. It's a plexiglass box on the interior and the larger box on the outside. They're both made from plexiglass, very cheap, easy to make. The box inside has the moth, and the box outside collects the water. This is the experiment that we have run in Arizona using 1 kilogram of moth. And you see here, this is pictures of the walls of the outside box showing water droplets forming and running down, and we collect the water. So for 1 kilogram of moth, we were able to collect 200, depending on the exact weather conditions, to 300 milliliters of water. Okay, so that's one cycle between day and night. Okay, so at night you're exposing the moth, taking up the water. During the day you're releasing it, and the moth stays in the device, and you can use it again and again and again. Our idea is that the moth is used over and over again. It takes up the water, releases the water. You can collect the water and use it, and then you can start the cycle again, and the moth can stay in the device for many years. The current idea is that we have done enough cycles that the moth can stay in the device for at least five years, as I will show you shortly. But this was a very successful experiment, because now I have a bottle of water produced by just having a kilogram of moth sitting there and no energy input aside from sunlight. So the water is pure. It contains absolutely no contamination. It's distilled water. And Eugene volunteered to drink it.
Nice.
All right. So we tested the water, and it's pure, which means that the moth is acting as a container to trapping the water, and it is not contaminating the water at all. So the water, to be drinkable, of course, it would have to be mineralized, but one can use it for drinking, and if you so desire, would be mineralized, but also one can use it for agriculture and many other applications, just pure water coming out of the moth.